Hello, my name is Marion. I'll be speaking about bubble struggles about call graph visualization with Radare2. I've been last year in 2015, and let me ask you, how many of you are French in the audience? Some hands up. Okay, hello. Yeah, it's my favorite nation next to Austria for your beautiful malware. Right. I'll be talking about call graph visualization, and I came up with the title because I was in a hurry to submit the talk, and I'm not very proud about the bubble struggle title. So I decided to give myself a more interesting title myself, and called myself Graph Dracula for today. I'll be showing you how to extract interesting information out of call graphs about binaries that you might be analyzing with Radare2. My full name is Marion Marschalek. I'm a malware researcher. I'm currently working as an independent contractor. I'm based in Austria, Vienna, and I'll be speaking about why static analysis nowadays is king. Or in my case, maybe rather princess. I've been analyzing malware now for 6 years, and I'm by nature rather lazy. And when you look at lots of binaries, you keep seeing repetitive patterns. Like, in fact, I believe the malware code that we see today is a large amount of binaries that all is based on some very few entries on Stack Overflow. So I really do believe that the large portion of malware that we get to see nowadays is really rather stupid. Still, we spend a lot of our rather expensive time on analyzing these binaries and trying to find out what they're actually doing, what they're all about. So lots of us use sandboxes to analyze binaries and to extract information about what they intend to do. And if you think closely about sandboxes, they are not actually all that well fit for analyzing lots of binaries automatically. Why is that so? Why do I think that static analysis is more important? I prepared this beautiful animation for you to understand of why I started this project for static analysis. I spent a lot of time working in incident response, and if you get to an incident response site, your customer usually thinks he's been hit by the most aggressive nation-state malware. The sandbox that you feed with that malware usually shows you that it's probably packed or shows some evasion. Then it shows you the setup of the malware. Then it shows you that it calls home, and then things start to go sideways because, as I said, sandboxes are not usually built to analyze entire binaries. A sandbox, by nature, can execute an executable that you hand over to the sandbox, and it can show you what the binary wants to show, which in the case of a standard remote access tool or standard banking Trojan is usually the setup. So this is, in very many cases, all that you see. This is especially true if you look at DLLs or plugins, or also if you look at GUI applications. Working in incident response, I also very often had the problem that we were handed over supposedly benign files, and the customer would ask us, can you prove us that these files were not compromised? And we were there sitting with the sandbox, and I was like, no, like the sandbox can't actually tell you whether there's no malicious code in there, because it just tries to find malicious code. But if the sandbox doesn't find malicious indicators, you still can't tell whether the binary was actually compromised or not. Finally, what do I think? If I'm handed over a piece of binary from an incident response case, I usually start thinking it's ransomware, because it feels like 95% of all cases, it is actually ransomware that you get handed by a customer. And finally, what the malware really does is, well, a lot of things that you won't be able to see with the sandbox or with dynamic analysis in total. If you think about the classical remote access tool, the authors usually try to fit as much functionality in there as possible. So usually they feature a keylogger, or they can take screenshots, or they can take audio captures, or they can send random information from the computer back to the CNC server, or they can receive commands or receive fresh binaries to execute and do whatever the author wants them to do. And this is something that I didn't see any sandbox ever telling me. This is why I came up with a tool built on Radare2. I try to disassemble entire binaries and extract information about that given binary. This is the GitHub repo, and here's the link to the GitHub repo. I call the tool R2 Graffiti due to lack of better naming. And what it tries is it disassembles the file, tries to find the functions within the file, tries to find the cross-references within these functions, and tries to find the API references, so the references to symbols within those functions, and reference strings to add information to the actual call graph of the binary. The tool is built for Python 3. I'm a Python 2.7 person, but I was told that Python 3 is the future, so it's Python 3 compatible, but should also run with Python 2.7. It uses Radare2 and R2 pipe. You wouldn't believe how many weird looks you get when you tell people that you actually work with Radare2. I've also attended the talk yesterday about Beancat, which I thought was an excellent talk, but I do not agree with the speaker saying that no one is using Radare2. Like, there are certain use cases where you can use that tool as well. The call graph is persisted with NetworkX. NetworkX is a graph library for Python, so you can technically use any data that you can represent as a graph and store as a NetworkX graph, which is very useful. NetworkX also supports a lot of algorithms that you can apply for extracting information and so on and so forth. So I personally have to say I'm not a specialist on graphs. I do not think at the university I have ever heard about graph theory itself. If I did, I do not remember. And this is actually also not quite that necessary if you want to just create the graphs for visualization. Moreover, if you have such useful binary libraries as NumPy and PyDeep that help you analyze the graph automatically. Also, rather irrelevant to this talk here, there is a connector for a Neo4j graph database, so you can actually persist the graph in a database and extract it from there again. Okay, so much about the tool. Radare2. Why did I use Radare2? There is a stack of reasons for using the tool over other disassembly frameworks, and a stack of reasons why you would not do this. My reasons were it's scalable, it's open source, I can pull up as many instances of it as I want, and it's scriptable. It's like fully based on the command line, so I can, in theory, pull up, I don't know, 500 parallel instances and start disassembling en masse. I haven't done this yet, but I wanted to keep that option an actual option. Also, they have great support and quick bug fixes, which they need, and I will talk about this in a minute. On the other side, as of rather recent, I believe they support analyzing entire binaries, which is a thing that many other disassembly tools that I looked at do not support. So Radare provides an actual interface to an analyzed binary where you can extract things as cross-references and symbols and strings within the binary with very simple commands. The commands I've listed here. Don't look too closely, they're rather quite confusing. But this is the stack of commands that I needed for creating my graphs. People kept telling me that there is a rather steep learning curve to get to Radare. And I tell you, I just skipped that learning curve. Like, I didn't try to understand the actual commands that well, but I usually go away, I post my problems to the Radare Telegram channel, and the Telegram channel shoots back command lines. That's how it works. You can try to read the documentation. There is documentation for the commands, but not for all of them. And sometimes you have to combine the commands to get to the actual value that you want to get out of the binary. Then it's very hard if you don't want to read all of the documentations for all of the different commands. Radare is very nice because you can concatenate commands. So you can say A for analyze, X for cross-references, T for I don't know what, and J for JSON. And then you get all the cross-references for a particular address in a JSON format. This is how the Radare command structure works. And this is very hard to understand. So I decided I wouldn't. Although Radare is a very nice project, so I met lots of their core developers, and they're actually really nice people. Like, there's people behind that project, for real. And they also really like to talk about their project. They're actually actively working on it and trying to improve it. And one of the reasons why I decided to use Radare was because I wanted a disassembly framework that works. I didn't realize when I started on it that it's actually the user base. It uses a tool that creates the quality output because they bug the developers to improve their tool. So this is one of the reasons why I think that more people should use Radare2. However, for my project, there's one single feature that I needed, that was function detection. Function detection is key for creating call graphs because you need to know the functions so you can find the edges, and then you can create an actual call graph. So if you don't find the functions, you don't get a call graph. It's as simple as that. So I did some testing on the function detection from Radare, and it's a thing, they don't have an out-of-the-box analysis bootstrap for PE files, but you have to feed it certain commands and configurations, so you will actually get there. And once you did it, the function count more or less correlates with the other disassembly framework that lots of people use. I didn't dare to put the name on the slide up there because I didn't want to have any tomatoes thrown at me on stage. So I just call it the other disassembly framework. And the other disassembly framework produces very good function detection output. So the quality of their disassembly is a very high standard. So I dared to compare Radare2 to the other numbers. And it turns out for 32-bit and 64-bit benign files, the function detection is slightly off. Like Radare finds more functions for the reason, like on the one hand, for example, they define exception handlers as dedicated functions, while, for example, Radare will inline them in the function or show them as part of the actual function that references the exception handler. But also, they have a bit of a problem with data structures. So if the compiler decides to inline data with the code, Radare doesn't necessarily figure out that's data structures straight away if it doesn't search for these particular data structures. So for example, jump tables, it will find properly, but if you have strings or other data mixed within the code section, that's an issue. But it turns out that this is mainly an issue with benign files, because if you look at the numbers of malicious files, you will find out that these are much more compliant with the other disassembly framework. Also, overall, malicious files are altogether a bit smaller than benign files, for obvious reasons, and they're easier to analyze with Radare2. R2 has a bit of a problem with large binaries, so if you feed it a binary like, let's say, a bit bigger than 2 megabytes or up to 4 or 5 megabytes, it will take a very long time for it to analyze the actual code section. It has a benefit, though, if you feed it very small files, such as most malware binaries, because it doesn't have to open up a GUI. This, I realized when I made these comparisons, like with malware, Radare would be faster, and with benign files, IDA would be faster. Again, obvious reasons, the GUI of IDA is a bit unnerving in analysis tasks. Okay, so here's where I started from. Now, let's talk about the graphs. The tool searches for functions, as mentioned before. These are used as nodes, and searches for cross-references among those functions. These are used as edges. The references by themselves are used two different types, like references from one function to another were one type, but references outside of the actual code section are indicators for me that there is dynamic initialization of actual executable offsets, like, for example, dynamic API loading. And I also store that information alongside the graph data. Yeah, as I said, we have nodes that are the functions. They have, of course, an offset, they have size, and they have a calling convention. The edges are either calls or indirect calls. Indirect calls meaning references to code that are indicated by jumps, for example, where the actual target of the call was initialized dynamically. I make a difference between those two because the direct calls are rather trustworthy, while the indirect calls aren't entirely trustworthy, because it could be that a dynamic target that I resolve in my parser at runtime possibly contains different offsets that are very hard to verify statically. So sometimes I miss those edges, and sometimes I have those edges to only one target, while there's actually different targets that are initialized dynamically. And this I can't find with the parser in a static way. The strings, if you've ever analyzed malware from a, let's say, very unconscious author, you might realize that if you just only look at the strings that the binary exhibits, you can actually derive information about the behavior of the binary. Very often they show, for example, CNC commands that are stored as text, or the names of APIs that are being loaded dynamically, and so on and so forth. So if you just look at that list, you might find out what the binary is actually doing. Therefore, to preserve such information, I parse the strings out of the binaries, and the beautiful thing about call graphs is that they offer a certain level of evaluation of the strings that are referenced. So if you have a string, if you parse a string out of the binary, you can't naturally know that it's a real string, because for example, the strings command doesn't offer any logic to say whether this is a readable string or actual garbage. So there needs to be some evaluation, and the cross-references within the call graph offer such evaluation. Like if you see that string is actually used within the code section, you have reason to believe that it's an actual string constant and not garbage data that's parsed out of the binary. What you can also do, what I will be talking about a bit later, is you can apply character frequency count. This is something I learned when doing cryptanalysis exercises, like very simple brute forcing cryptanalysis, like, for example, a simple XOR or something that's actual cryptography, you can still brute force. And then you have to evaluate the output of your brute forced results. And that's frequently done with character frequency analysis. So you see whether the characters that are contained within the result actually comply to some spoken language. There is a table of character frequencies for the English language that I adapted to binary needs. As I said, I will be talking about this in a minute. Then another challenge that I found searching for strings was the detection of string lists. Frequently strings are stored as a list within the binary and referenced at runtime like dynamically by index. And this is a problem if you evaluate them by cross-references. So if you trust the cross-reference, you will only see the first string that's referenced, but not the list that's following after. And to counter this, I built some string list detection where I just follow down the strings and see how many readable strings I can find that follow my reference string. Now finally, what's the information you can gain from strings? Of course you can read them. Like if you visualize a graph and show all the strings, you can read in the graph which string is being referenced. But there's more to those strings. Like I started that project partially for analyzing targeted binaries, and they frequently come without runtime packers, but they like to apply string obfuscation to hide their initial intents. So one of the important information that you can gain out of strings is how readable they are. How many readable strings are there? And is the amount of readable strings enough? Or could you imply that strings are being obfuscated within that binary? Furthermore, the APIs. Here's a screenshot of how Radare2 shows symbols within the binary. And all I did was just walking down the cross-references of symbols that Radare would spit out to find my API calls within the binary. Therefore, again, we have the problem of indirect calls. Like frequently, you will find not a call instruction when looking up the cross-references of a symbol, but you will find a move or a load instruction or something else that dynamically assigns the offset of the function to a register, for example. And then you have to follow down the graph where this register is actually being accessed to find out where it is called and more importantly, how often it is called. This again is useful because this is frequently done, but it also implies some certain errors. If the APIs within that register change, you still only see the call EAX, for example, but the value can change at runtime, and this is very hard to find out statically. Finally, what I had to apply was some sort of thunk pruning, because a lot of thunks induced by the linker are an issue with call graphs. They blow up the call graph and show you lots of APIs that aren't actually being called in the binary, that just exist within the thunks. And of course, dynamic loading is an issue. So if the malware decides to dynamically load its APIs, for example, through load library and get proc address, you will not be able to see this in a static manner or not very well. But what you can see is that it's happening. So this is one of the interesting features that I found I wanted to find out about the binary, whether it tries to dynamically load APIs that I would have to analyze further. All right, finally, how do I deal with other indirect calls? So for example, there is APIs like create thread or set Windows hook X that use certain handlers for executing their functionality. Like for example, if you see a keylogger, most of the keylogging functionality will be hidden in the hook handler of set Windows hook X. And this is difficult to find as a call cross-reference. Like you will have a function cross-reference in the code, but you won't see that being called, but being pushed on the stack or otherwise processed. You have to follow that down with particular interest. And more importantly, I tried to do a bottom-up sweep for indirect calls, looking at all the disconnected nodes that I had and trying to find their cross-references in the call tree. This is also rather quite error-prone, because if you see a cross-reference, like a data cross-reference of a function offset within the trace, it still doesn't mean that the function there is actually being referenced. It's just an idea that it belongs somewhere in that area of the code. So these edges are particularly tagged as being indirect, and that has to be considered when looking at the actual visualizations. All right, so much about the parsing. Finally, the graph structure. I did that slide this morning. I just copy-pasted the documentation out of my script. But the main idea that I wanted you to get was that there is the functions as node, of course, There's function references and indirect references as edges. There's API calls as attributes of the node stored within the node. And there's strings also stored as lists within the node. I'll later be speaking about transformations of the graph structure to get out specific information from the APIs and strings in particular. And now finally, I started this project not with the idea that I needed to visualize my graphs, but I created visuals to improve the quality of the graphs. So I started with visualizing the structures as dot graphs to see what's happening where and whether my parser actually had the right output. So whether I found all the functions, whether the functions looked like they were supposed to look at. And whenever it happened that I talked to people about the graph project, they were expecting to see visualizations, because what else would you do with a graph structure? So yes, finally I started to visualize them, and that's why I'm here today. But as I found out, I had started to visualize binaries way earlier than when I started the project. This is my left arm. This is a jump table that I analyzed in 2013 that I found very particularly hard to analyze. So this is a visualization that I did years ago. But you'll find out that this is not utterly useful. Because useful ain't easy. That's something that hit me first when I tried to do machine learning on binaries, and it hit me again when I tried to do visualization on binaries. There's a lot of options, there's a lot of tools, and you can try a lot of things, and you will get a lot of graphs. It just doesn't mean they necessarily tell you anything. So as I said, I started the project with visualizations in dot, and it turns out that dot is like a tree structure, so you can put all the nodes as a tree together, and with small binaries it works very well. Like you get small trees and you can follow down the tree and see the paths perfectly well. But as soon as the binary gets like reasonably big, let's say some 100 kilobytes, the graphs will look like this. This is a piece of ransomware. Usually marketing departments get very excited when you tell them you visualize. I showed that to the marketing department of my former company. They were not excited. So what can you do with the graph to make it actually useful? Well, first of all, there are certain attributes of a graph depending on the visualization algorithms that you apply that you can see at the first glance. This is very simple. Like, for example, you can see whether it's a large graph or a small graph, or a dense graph, or a very loose graph. Or you can see whether you have subgraphs that are disconnected. Or you can see whether everything's very well connected. That gives you a base idea of how much code is there in there. An interesting case was the recent WannaCry ransomware. If you look at the call graph of it, it's like, I think, 10 nodes, but the binary is, what, I think a megabyte or some 100 kilobytes. So it's like very big, but with very little code. And if you look at that, you can retrieve the information that there's a large resource section in the binary. But that's like very simple information, and you don't necessarily need visualization algorithms to find it out. What's more interesting in particular, with a static analysis tool, you will finally have a way to look into exports of a DLL. No sandbox I saw ever is able to automatically analyze every single export of a DLL. You have to, there are some where you can configure which export to call and which arguments to hand over, but they won't like show you automatically. So with this tool you can. Also you can finally analyze GUI applications, which in the sandbox is also rather quite tedious. You can see spaghetti code. I swear if you look at malware, you will see a lot of spaghetti code. And I started thinking that most malware is actually copy-pasted from Stack Overflow, because you also see a lot of similar spaghetti code. You see copy-paste code. If you, for example, see a large graph and then a small graph next to that large graph, you can retrieve that this was not actually developed within the former code base. You see that in a minute. You can very easily spot packed code. A while ago, I asked someone working on runtime packers how he actually retrieves his packed samples and how he verifies that they're packed, and he said PID. I don't know how many people have ever worked with PID in this room. Are there some hands? Okay. PID works with signatures for entry points. So there's a stash of signatures, byte signatures, that are compared to the entry point of the binary. And it doesn't matter how often I tried PID, I always find out my binaries are Armadillo packed. So something's clearly wrong with that signature matching approach. Anyway, we also see repetitive patterns and noise. So let's get to the visualizations, because that's why I'm actually here. A simple visualization with dot algorithm again. You can see again the tree structure, but with certain highlighting features. You can see whether there's bigger nodes and smaller nodes, saying that they have a high out degree or low out degree. And with the coloring in this graph, you can see how many API calls are happening within the particular nodes. So you can, for example, spot a certain area of the graph, like highlighted here, that is of particular interest to you because there is highly interconnected and has a lot of API calls to show. As compared to that, if you look at a graph that does not exhibit a lot of API calls, you might be able to spot a subgraph like down here, the green one. Green in this case means there are 0 API calls happening within that node. And in this case, we have a large subgraph that's rather quite disconnected from the main code body up here, which doesn't show any APIs. And I just see that you can see edges on here, like this gray mist in between, that's the edges. Anyways, as I said, dot is not very useful in visualizing large binaries. So one thing that I was working with was a particular highlighting idea. This is just a sub-project of the actual graffiti tool. It's a transformation where you can feed particular items of interest to the parser that will be looked up in the graph and then highlighted in a visual way. So for example, you can start searching for particularly formatted strings or a family of API calls. This visualization here shows you a count of any API call that contains the string alloc in one or another way. So you can, for example, search for memory allocations within the binary, or search for, I don't know, strings that contain the word error, or strings that contain the word C and D, or whatever you like. So you could just highlight. But then you still have the problem that the graphs get really huge, and you have to find a way to make them more feasible. So how to deal with large graphs and too much information? That was the main issue that I faced. I had to understand the data that I had to find out what I actually wanted from the data to be able to visualize that. I found out the biggest problem you'll face with call graphs is data reduction and simplification. You have to know what you're looking for, you have to know what your data supports, and you have to know what your algorithms and your visualization tools support. This doesn't always comply. So I once had a customer who would hand over a stash of binaries and said, like, this is his APT that hit him, and he wants me to derive a timeline of how the attack happened. And this is something that clearly doesn't work. Like if you enter a project with these kind of ideas, you won't get very far. So this is why I formulated certain goals. Like I wanted to work with layout algorithms to simplify my data. I wanted to use graph transformations to find the interesting bits within the graphs, and then work with API gadgets and highlighting to show that in a visually nice way. And as the last point, I'll show you what I did with the string constants, because the string constants don't really go well with the graph visualization. First of all, one of the algorithms that I used that didn't turn out like extremely useful but nice to look at was the Fruchtermann-Reingold algorithm. It's terribly German. By the way, the tool that I used mainly for visualizations is Gephi, which is now like the shining star for graph visualization. It's really nice. It's rather fast because it's able to leverage your GPU for graph calculations, but it's also built in Java and it's not quite interactive. More about this later. So with this algorithm, your graph is built in a circular way, which helps you get an overview of all the nodes within the graph. And you can quickly spot particular fields of interest, which again in this case would be the exports of the DLL that was analyzed. They're highlighted in red, and their name is shown on the graph. But also you can see that, I'm not sure you can see that here, that these three exports all call this one node that's here highlighted in yellow. And that's bigger because it has a high out degree. It's yellow because it's a thread handler. So for me, this would be the node where I would start my analysis, because it's the most outstanding node within that graph. Well, this is interesting though. The algorithm takes rather a long time to be calculated. So I found out this is rather tedious, because for every node whose position is being calculated, all the other nodes in its vicinity have to be recalculated. So every switch of a node needs the other node that was at the position before to disappear. It's rather funny to watch being calculated dynamically, because you see all the nodes like popping around, but it takes forever. Although the idea of force-directed layouts is exactly what we need when looking at call graphs. What's a force-directed call graph, force-directed layout? Directed, in that case, means that the algorithm seeks to cut all the edges to an equal length, and then tries to have as little crossings as possible. That's the base of where we're starting from. And then, of course, the algorithm applies forces that work out particular areas of interest. In my case, that was the out degrees. So the more out degrees a node would have, the shorter the edges would be. And this applied to all nodes within the graph. Help showing density, which you can't do with the tree structure or with the Fuchtermann-Reingold algorithm. So this kind of density is what helps you group certain subgraphs in the picture. And this is what we're going to look at now. Yeah, of course, also it has a high running time, and it requires a lot of iterations, which is why this algorithm is rather useful applying to a graph that you really want to analyze. For a quick overview, it's rather tedious. How does it look like? So this is an example of a call graph for a rather small binary. It's, I think, a rat that was used by Sophisy, maybe. That was my favorite test set, by the way, because Sophisy used a lot of binaries in the past, so it's a large test set, and they're usually not packed, which is also very nice for the call graph generation. Force Atlas is a force-directed algorithm built into Gephi. It supports a lot of different parameters that you can change, where the most important ones are repulsion and gravity. These two parameters help you format the graph either in a very dense way or in a very loose way. The very dense way, shown on the left side, over here the right side, help you find particular subgraphs in the binary very quickly, because it separates the different clouds of nodes, but it doesn't help you get a very nice view of the nodes themselves. In turn, if you modify these parameters, the graph gets more loose, and you get a particular view into the different nodes. By the way, what I didn't do in these visualizations, of course, you can also add all the text information for the specific nodes. So you can add the offsets and the size and the API calls and the strings, which, while adding all the strings for all the nodes isn't very useful in the visualization in the first place, but I'll show you how to make that useful as well a bit later. What this algorithm is very useful for is most specifically in finding copy-paste code. This is nicely shown on this binary that also belongs to the Sophisy family. I just see that these graphs look very, very bright. Anyway, so you can see that down there in the bottom corner, there's a subgraph that looks like standing out of the rest of the bubble. And if you have a closer look, you can highlight these subgraphs, and if you have a closer look at the edges, you'll find like one edge that goes towards the subgraph and all the other edges that go towards the main code body, probably using libraries or using other functionality provided by the main graph. This is how you spot copy-paste code within a call graph. Furthermore, you can see on that picture, again, the darker the node is, the more API calls it contains. If it's bright yellow, it does not contain any API call. So you can see that this subgraph that was copy-pasted in there does not contain any calls to OS-provided APIs. This doesn't necessarily tell you that there's something wicked going on there, but it gives you an idea that in there might be code that processes data or modifies data or might encrypt or compress or decompress or decrypt data that is being used by the main graph. With that in mind, I decided to look a bit deeper and look into mnemonics that appeared in such subgraphs, because usually, so I'm not a specialist on crypto either, but I can see when crypto is happening in a binary, because I see a lot of funky instructions that usually do not happen in productive code. So there I usually see a lot of shifting and rolling and arithmetic operations that help modify tiny values. And if you look out for these instructions, you're able to highlight the density of arithmetic instructions that help you find algorithms. A nice example for this, and this is why I asked how many French attendees are here this year. A nice example for this was the Babar malware that I talked about 2 years ago. Babar is an espionage Trojan that would, for example, try to tap the computers, like the victim's microphone, to record audio from what's happening around the computer. And they used a particular audio codec that was, I suspect, also copy-pasted into that code body. And if you highlight the density of arithmetic instructions within the code, you'll very, very clearly see that the audio codec is bright yellow like a torch as compared to the rest of the binary. Now if you have a closer look at the edges as well, you will find out that there is exactly this edge that goes up here. That's the entry point to the algorithm, and the other edges all go towards the code body, which probably means they leverage some library code that's compiled within Babar. So this way we can clearly see this audio codec in the binary. This is still a proof of concept. So far I've tried this on Babar and it worked because I know that Babar has this audio codec. I'll have to find more binaries that actively leverage audio codecs and their own cryptography to be able to say more about whether this works or not. There's also, by the way, an issue, like I thought I'd look at ransomware and find a lot of algorithms, but turns out that most ransomware that I parsed actually uses the Windows APIs. So they're not really happy to cook their own crypto, I feel. It's probably better that way. All right, after algorithms, what else can we search for? I told you that I add the API calls that are happening within the function as attributes to the node. And of course, we can search these. It's not actually feasible to, or in the base structure of the graph, it's not feasible to visualize all the calls for all the nodes because you just get a stack of text in a circular format. So I decided that I would create a more dense view of the APIs. This you can do when you map certain API combinations into actual behavior gadgets, as I call them, where they are not actually behavior, but some certain sets of functionality that the API calls represent. This is more of a, this slide is more of an illustration. The set that I have on there is not actually finite, so I just took some samples and created some gadgets. If you're working on a particular set of binaries that you want to highlight visually their behavior, it is more feasible to go analyze the binaries, extract the behavior gadgets that they exhibit, and create your own gadgets for scanning. The thing that I found out, which was also rather interesting by itself, if I scan for particular behavior gadgets as I thought the functionality would be implemented, I would quickly find out that some authors implemented slightly different, and I wouldn't find that. That was very interesting to see how, I believe that a software developer has his own view of how to implement certain functionalities, like he will implement a keylogger, how he thinks the keylogger should be implemented if he didn't copy-paste it from Stack Overflow. And in the end, by these little glitches, these little differences, you might be able to create actual signatures for the authors who implemented certain functionalities. All right, but how does it work? So I have these lists of gadgets, and then I just go scanning through the graph. This is surprisingly fast, even for large graphs. So you look through all the API calls in your graph and search for the first pattern contained within your behavior gadget, and then start in a circular way to search around this node to find the actual entire gadget. And once you found the gadget, you can tag the node and say that this node has found this particular gadget, and then you can highlight them. This could look as follows. So this is one of the classical ruts that I parsed. It shows a lot of threads that it creates, a lot of files that it reads, a lot of APIs that it loads, and for me, maybe most important, the screenshot that it takes. So this is the text format of the behavior gadget that you found, but the text isn't nearly as interesting as the visualization. This is a piece of malware that I compiled myself because I wanted to try how the actual crooks are working and copy-pasted code from the internet. It's also rather spaghetti format. So, again, I'm not good with crypto, I'm not good with math, and I'm also not a software developer. So I really just took that particular code. And when you visualize it, you find out that it has a large code base, but only a very small part of the graph actually exhibits behavior gadgets. This is the white. Oh my God, that looks terrible. I wish you could see my screen here. It's beautiful. Like the background is black, and the functions empty of API calls are visualized in red. Mainly this here is large API-free cloud. And down here we have a small API-free cloud. And here you see a subgraph, or maybe you don't see a subgraph, but here is a subgraph exhibiting a lot of behavior information. You can see if I zoom in, yeah, that's better. You see all the behavior gadgets and how they're tagged for the node. So you can, with these gadgets, it's actually feasible to visualize the text in the graph because you can still read it. As opposed to if you would visualize all the API calls themselves, you would have like a never-ending job in just reading text. And what can we see here? Again, we have this large graph. We have a lot of noise up here, which I found out is not a very huge compression algorithm, but actual library code. You can also see, or I can see here, that this is, it looks like a separate graph from the actual behavior graph. So you can probably spot that there is all the library code, and then very densely, very loosely connected the behavior code that references the library code. And this way, I mean, of course, we can detect library code in binaries with signatures and whatnot, but sometimes it's very hard, like if unknown or code that you don't have signatures for analyzing is compiled within the binary. You find just large stacks of, for example, OpenSSL. And I don't know how many of you have ever like tried to analyze the MD5 algorithm because they didn't have a signature. Maybe not so many. Yeah, if you once did this, you spent a lot of time for nothing, just to afterwards find out that it's library code that you could like just have read on the internet, where I find the sources. So I think in larger projects, the visualization could actually be used to find library code within the binary, so you can find out where you have to start your analysis and don't spend too much time on code that's actually documented somewhere else. Here's again the gadgets. And also there's like, again, the node size is the out degrees. You have this large node here in the middle that also features a lot of behavior gadgets, and you could just think that it might be feasible to start analyzing there. Of course, you can also color code your functionality families, and in the end, I found out this is where marketing starts to faint. If you give them a graph like, look, this is the malware, this is happening here, this is happening there, and it has 5 colors instead of black and white. That's cool. Another feature I built, though, as I found out the graphs are still too large. Of course, it makes sense to look at subgraphs. So if you found out you have a node that's of particular interest, you can hand it over to the tool, and it will create a subgraph starting with that tool. So this is then starting with that node. So this is then your super node, and all the edges that are referenced, or all the other nodes that are referenced, will follow in the visualization. This looks like you. Oh yeah, this can be read. So in the center of this graph, you can see the node that I picked as of particular interest. And if I just slide back shortly, you can see here is a node that says API loading. This is our node. So I saw that and thought there's API loading happening in that node. And then I looked at the subgraph and found out there's strings in there that look like user32 DLL and get user object information and get active window and get last active pop-up. These are strings that are referenced within the binary, and you can also see the APIs get proc address and the library being referenced. So you can actually conclude that this function will load exactly these APIs and use them later on within the binary. But of course, this transformation also makes sense for the binary as a whole. It is sometimes useful to not look at the node distribution, but also look at which strings are referenced where in the visualization. As I said, displaying them as text, as node attributes, isn't always useful. So I put the transformation to just span the graph open as a tree, creating a super node that would connect all the unreferenced nodes within the graph, and expand the APIs and strings as dedicated nodes. This makes the graphs exponentially much bigger than they were before. This isn't always useful. But there was one interesting case where I thought it was hilarious. I looked at the binary that I've analyzed some years ago, and I know that it does dynamic API loading. I know that because I have its jump table tattooed on my arm. So I remember that there was no API references within the binary, and what I didn't remember was that there were a handful of them still in there. So if you look at that graph, you might see some nodes, like here's one in red, here's another one in red, here's a group of them in red, and here's another group in red. So red in this case is API calls that are now displayed as dedicated nodes. And if you look closer, there's one that looks like it's library code that, of course, wasn't obfuscated by the author. But if you look at the second bunch, there's also something that looks like it just forgot to obfuscate a group of API calls. If you look at the bottom, there's load library and get proc address. That's the jump table that's being built. And if you look on the right side here, you see APIs that suggest that something graphical is happening. Maybe a screenshot is being taken, or maybe a picture is being changed. So these API calls are in plain within the binary, and the visualization tool helps you find exactly these bits where the author forgot to obfuscate their API calls. This is something that's not all that uncommon. Malware authors are also just people. Some of them are more practiced than others, and all of them have forgotten something in their life at some point. So if you get a conclusive overview over the entire binary and know what you're looking for, you might find out that you forgot more than the obfuscation of a particular set of binaries. I would suggest that in this case, the module that does this screenshotting or whatever is happening there was copy-pasted at a later stage in time, and the guy just forgot to dynamically resolve these APIs and just left them in statically. And as I said, this is happening frequently. I also saw cases before where the author just forgot to obfuscate all his strings, and apparently left some strings unobfuscated, which gave me an idea of how to de-obfuscate the actually obfuscated strings. So this is very useful information to extract. One of the last graph examples that I have today is, of course, you can compare call graphs naturally. I don't know if you see it very well here. The edges are again disappearing. Like, you have to imagine lots of edges in here. And these are two actually rather equivalent binaries with different hashes, of course, that if you visualize them, you see that they are more or less equal. And you can also see little differences within the node structure. You can see that here you have a couple of bigger nodes that you have here as well, but if you count them, you'll find that there's a difference, and you can get an idea of where functionality was added within the graph and start looking there to find out what that was. Let me say that graph diffing or similarity research wasn't actually a goal of this project. It just kind of accidentally happened. So if you have a small to medium-sized group of samples, you can visualize them all and just look at the pictures to see which is the most interesting one where you start. This is very important in incident response, that you start at the important stuff and not at the unimportant stuff, because incident response is usually a very nervous sport, I would say. Like, you have to be very fast and have to get information just like yesterday, so other people can start to clean up the network. Okay, but the tool also spits that out in text format, which I found a lot more useful for comparison of stacks of binaries. By the way, lots of these examples and also the text format of some of the projects are published on GitHub if you're interested in text or pictures. Finally, the last thing that I tried to visualize were the strings. I could, of course, read through the strings referenced within the binary, and I would get an idea of what was happening there. But there's very little options to automatically evaluate strings that are being referenced. Of course, you could use a dictionary to try to extract information from the actual words and interpret their meanings, but still rather quite tedious. What was it, though, that I thought you could figure out just looking at the strings? Yeah, first of all, I already mentioned human readable strings give away information just by being there. So if there's no readable string in the binary, you get an idea that the binary tries to hide something. And finding out that the string that you have is actually human readable isn't that easy either. The graph structure helps you, though. So I found that I get, also if you're interested in malware machine learning, I found out that if I look at the cross-references, I get a set of actually relevant strings as opposed to all the compiler-induced and random strings that are being parsed out usually. But also, as I said before, if you look at the character frequency count of the words of your string, you can find out how readable or how understandable the string constant is. And that looks as follows. So in this case, I used a binary from the Cheshire Cat family. Here's the Cheshire Cat. Cheshire Cat is malware that's really, really crazy. If someone searches for a challenge, I'm happy to share the binaries. But also, the malware would exhibit a stash of readable strings that would give away information. And if you now run the character frequency count on these strings, you find out that at an edge of about 0.04, the strings start to become readable, and everything that's below that edge might not be that useful in your analysis case. This is useful, but a bit problematic if you have short strings. As you can see, there is one up here's the pointer that says %08x. That's obviously doing something with string formatting. That's still a useful string, but that would not be evaluated correctly by the character frequency count. Also for the evaluation, I don't use the standard English language table, but a modified table that's more accurate for strings that you find in a binary. Because the table, for example, doesn't consider numbers or slashes or any printable characters that are not A to C, basically. So I have an extended table. And what can I finally do with these numbers? Again, I have a stash of float numbers. Well, for once, you can start visualize the strings in a nicer way. Again, your marketing department will faint if you give them these pictures of the malware. But again, this is not entirely useful. Like you can see, you can browse through the strings that the malware exhibits and can read them like in a graph way instead of a text output. But we still have the problem. We have to make that more useful. So what can you actually do with these character frequency counts? Like, for example, if you'd be interested in comparing the samples, you can calculate a distribution of these frequency counts. This works the following way. Like you have a list of numbers of different length, and you just see how many numbers fit into different buckets. The buckets that I defined for my histogram data structure were 0.01 numbers wide, and all the values that fit into this bucket were put into the actual bucket. So you can see this is a test set of Sophacy. Again, a stash of numbers. And with this stash of numbers, you can then start to visualize these numbers. I died when I found that graphic, literally. So if you have a sequence of numbers, you can visualize them as a distribution. I found the histogram is most useful for my case, because I don't really do well with curves, but I do rather well with edgy structures. So I generated histograms out of the character frequency count of strings found within the binary. With this visualization, I can compare the character frequency count among different binaries and see how readable the reference strings are and how well they are understood by humans. But also you can see the edge I mentioned before, like the fourth edge inside of our histogram. In this case, it's the green one. So everything that's above the green line in this case is, so to say, readable strings. So everything that's above the 0.04 is considered readable based on the tests that I ran. And everything that's below is either garbage or obfuscated or not that readable in that case. So here's, again, some Sophacy binaries. They look rather readable, but if you look at the different sample set, you'll find out the strings are not that readable. These samples were not packed, I verified. They exhibit nice code structures. They just don't show any readable strings that are referenced within their code section. So you can see that the green lines are rather low, and the amount of strings on the left side of the green lines are rather high compared to the right side. So this gives you an idea whether the strings in the binary are readable and how readable they are. All right, now my time is almost over. I have prepared a short demo of a project that I've been working on as well. Namely, the graph structures that you get out of Network X, you can transform them into any data format you want. And the most useful I found was GML that you can put into Gephi, which works really fast and you don't have to do much. But you can also dump them as JavaScript or as JSON that you can feed JavaScript and then visualize with D3. And D3 is just super nice in terms of animations, because you can update the graph as often as you want. It will always like pop back into form. I like it. But also, there you finally have the chance to create interactive graphs, which in Gephi is rather tedious. So now I have, for example, the lists of strings and character sequences and call graphs, API calls that the node exhibits on the left side or on the, whoops, what happened there? Why is my screen gone? That sucks. Anyway, I'm almost done. Imagine this to be super interactive. So if you know, just think it were. You can hover with the mouse over a particular node, and it will show you the list of strings and API calls that are being referenced within the node. It looks a lot better because now if you click on the node, the whole graph starts bubbling and wobbling, and it looks great. Marketing will die, I swear. Okay, now finally. Of course, the project looks a bit better than in practice it actually is, as it is usual with open source software. There is a ton of issues. For example, C++ exhibits a lot of indirect calls that I can currently not parse. I'm working on that. Visual Basic, .NET, and Delphi will always be a problem, like for anyone, anywhere. Other exotic compilers are potentially an issue too. Large binaries, as I said, bigger than 2 megabytes, are really hard for Radare to parse. Currently, they are working on that too. Like we're all eagerly working on these issues. And finally, loops and the total of inner programming logic you can't get out of a call graph. I had lots of discussions why I don't work on CFGs and control flow. It's a lot more data than I think is needed for getting a basic overview of the malware. That's why I work with call graphs. Now finally, if I have all these stacks of issues, why am I still doing this? By the way, if you go through a presentation and you search for graphics, you can just put your topic into Google, picture search, and add the word pun. And this is what you come up with. So why did I do this? I wanted to help in static analysis. I wanted to reduce my useless work time on boring malware and wanted to find the interesting ones at a quick glance. Accidentally, I also built a borderline foolproof packer detection. Because if you look at the call graph of a packed binary, you won't see any. I have an easy way to persist analysis results. So if I found out what the binary does, I can tell my visualizer to visualize that, and then I have a nice picture that I give to marketing, and they won't bother me again to write a blog post. And also, unintentionally, I have a disassembly framework bug report factory. So that's what I said in the beginning. If you want to play with Radare, I'd be happy to help you start on it, and also you will find the Telegram channel or the IRC channel very helpful, where they just spit out command lines. And the more users they have, the more bug reports they get, the better the quality will be. That's how the usual process is, and I think some of us would be very, very happy to have a very well-functioning disassembly framework that works on the command line. And as I said, marketing will love you if you visualize a lot. The tool scales as open source. You can download it from my GitHub. It's very lightweight. It's relatively fast if you don't put too much data in. And you can parse your binaries once, store the graph, and then analyze the graph as often as you want. That's rather quick. Finally, I think I have 1 minute left. Thank you for your attention. And if I have time for questions, I'm happy to answer. Thank you.
Hi. I'm just curious if you, in your graphs, or had done this or considered looking at the linear distance between functions as something to factor into your edge length, mainly because in your normal binary you have kind of similar functions in object files kind of close together, so you have your main binary made up of multiple different object files, so you might have you'd expect to have sort of clustering based on the nodes that are close together.
Oh yeah, sure. I mean, there's lots of ideas and lots of things still to do. I spend most of my time with data QA instead of figuring out how to make the visualization better. The thing is, there's lots of ideas on how to level up the data structure to get a more abstract view of what's happening in there, just for simplification. There's something you can do, for example, with the behavior gadget. If you find out where the behavior is located that you're interested in, you can level up the graph to purge all the nodes that do not contain interesting information, and just visualize the higher level that you extract from the graph. In general, you can transform the graph in any direction you want. In theory, you could also go down to the instruction level. Like if you say you have a subgraph that I found out contains a lot of information, I want to see what's going on in there. In theory, you could add the control flow graph or look at the instructions in the visualization. There's lots of options and too little time. As you said, for dense subgraphs and edge evaluation, there is a module from Network X that applies the force-directed layout graph from Gephi onto the graph that helps you search for dense subgraphs. I think that's what you meant. If you can spot the dense subgraphs and, for example, find the libraries that were linked, you could naturally get rid of this large bubble of nodes and replace it with like the information that there was a dense subgraph. That's totally possible.
Hi, can you give us an example of a disassembler bug that your project made obvious? You say that you have discovered an unintentional way to find bugs, right, with this project. What sort of bugs did you expose?
Tons. So the disassembler of Radare is not the problem. The disassembler works very well. The problem that I had was that the function detection would sometimes miss functions. That was then just like disconnected disassembly within the binary, or that they would disassemble things that were not actual functions, like data structures that the binary used at runtime. I don't know. I'd be very interested if someone's working or analyzing the Visual Studio compiler. I'd be interested which compiler settings are at fault that the compiler adds data within the code section. That's a big problem, not only for Radare, also other disassemblers have the same issue, that verification of a function that's being found is very hard. So whether it's a true positive or a false positive is very hard to tell. That was one of the issues. Another data formats, like I would often use commands in a way that looked useful to me, and then the Radare guy said, like, yeah, but you're overlooking that you have, I don't know, combined commands, and this is why your JSON structure isn't one string, but 25 strings, and you have to combine it back together. So, the function detection was the biggest problem. And then sometimes Radare just updates feature and destroys other features with that, and then you have to tell them, guys, your feature is broken. And they're very quick in fixing. This is the thing that I love about it, that you put in the Telegram channel, like, this is broken, and they're like, okay, update, it's done. So yeah, that was our bug fixing odyssey. Thank you.